What if you could shoot someone without ever seeing them, and without them ever seeing you? In 1943, Nazi Germany tried to make that a reality. They built a barrel that could bend bullets around corners. On paper, it was genius. In practice, it was one of the most spectacular engineering failures of World War II. Picture this: a rifle barrel that bends at a 30-degree angle. A soldier crouching in a foxhole, never exposing a single inch of his body above the dirt, and yet firing lethal rounds at enemies he can see only through a tiny periscope mirror. It sounds like something out of a video game, but in 1943, as the Third Reich began to crumble, German engineers were deadly serious about making it work. They called it the Krummlauf, literally the curved barrow, and it was designed to do what no weapon in history had ever done: let a soldier shoot around corners. The concept was elegant, the engineering was audacious, and the results were a masterclass in how desperation and ingenuity can collide to produce something simultaneously brilliant and catastrophically flawed. The Krummlauf was expected to fire thousands of rounds. The actual number it survived will shock you. And when American forces captured one and hauled it to a proving ground in Maryland, what they discovered about this weapon changed their understanding of what was physically possible and impossible with a firearm. This is the story of Nazi Germany's most ambitious ballistic experiment, and why it was doomed from the moment the first bullet entered the curve. By the end of this video, you will understand exactly how German engineers tried to bend the laws of physics, and how physics bent back. If you are fascinated by the untold stories behind history's most extreme weapons experiments, hit that like button and subscribe. We go deep on the engineering, the tactics, and the human decisions behind every story. Now, let me take you back to 1943. By 1943, the tide of the war had turned decisively against Nazi Germany. Stalingrad had been lost in a catastrophe that consumed an entire army. North Africa was slipping away as Rommel's Afrika Korps retreated toward its final collapse. The Allies were preparing to invade Italy, and the Eastern Front was consuming men and material at a rate that no industrial economy, no matter how ruthlessly mobilized, could sustain indefinitely. Germany's military doctrine was undergoing a fundamental shift, one that its own generals understood but could not publicly admit. The era of offensive blitzkrieg, the lightning war that had swallowed Poland and France and driven deep into the Soviet Union, was over. What replaced it was defensive warfare, holding ground, fortifying positions, buying time. Every foxhole, every trench, every bombed-out urban ruin became a potential strongpoint in a shrinking perimeter. And this is where the fundamental problem lived. Defending a position means taking cover. But taking cover means you cannot see, and if you cannot see, you cannot shoot. Every time a soldier raises his head or his weapon above a trench parapet, he becomes a target for snipers, for artillery spotters, for the relentless suppressive fire that modern warfare pours onto any defensive position it identifies. The same walls that protect you also blind you. The same trench that keeps you alive makes you useless, unless you are willing to die to fire back. This was not a theoretical concern. This was a daily reality that was killing German soldiers by the thousands along defensive lines that stretched from the Atlantic Wall to the ruins of the Eastern Front. Somewhere in Germany's sprawling weapons development apparatus, an idea took shape. What if the barrel itself could bend? What if a soldier could remain completely below cover and still deliver aimed fire at the enemy? This was not an entirely new fantasy. The idea of shooting around corners had been imagined before, in the trenches of the First World War, in the pulp fiction of the interwar years, but no one had ever attempted to engineer it at scale for a modern military rifle. The core challenge was staggering when stated plainly. A bullet travels in a straight line at over 2,000 feet per second. To redirect that bullet through a curve, without the barrel shattering, without the bullet disintegrating, without the whole assembly turning into a pipe bomb in the shooter's hands, is a problem that sits right at the edge of what metallurgy and ballistics can handle. And yet the engineers were going to try. Not because they were dreamers, but because they were desperate. This was a Hail Mary, an engineering moonshot born not from confidence, but from the creeping certainty that Germany was running out of conventional answers. The engineers needed a host weapon, something modern, reliable, and already in production. They chose what was arguably the most advanced infantry weapon in the world at that time. But how do you actually make a bullet turn a corner? The answer involved a radical early idea that sounds almost absurd, and a series of prototypes that pushed metallurgy to its breaking point. The weapon they selected was the Sturmgewehr 44, and to understand the ambition of the Krummlauf, you first need to understand what it was bolted onto. The Sturmgewehr 44, the Cent G44, was the world's first mass-produced assault rifle, a weapon that would define an entirely new category of firearm. It fired the 7.92 by 33 mm Kurz, intermediate cartridge, a round specifically designed to split the difference between a full-power rifle cartridge and a pistol round. It offered selective fire, meaning the shooter could toggle between semi-automatic and full-automatic modes. Its effective range stretched to roughly 300 meters, and it fed from a 30-round detachable magazine. It was a weapon so influential that its silhouette would be echoed decades later in the AK-47. The MG-42 machine gun was also considered as a secondary platform for the Krummlauf concept. But the Cent G-44 was the primary host, the weapon around which the entire curved barrel system was designed. The Cent G-44 was already revolutionary. Attaching the Krummlauf to it was like bolting an experimental jet engine onto an airplane that was already pushing the limits of aeronautics. Because the Cent G-44 was designed to fire in a straight line, what the Krummlauf asked it to do was something its designers never imagined. Here is the infantry variant of the Krummlauf, designated the I model. In full detail, the attachment consisted of a 14-inch barrel broken into 3 distinct sections. The first 4 inches were straight, clamping directly onto the muzzle of the Cent G-44, like a conventional barrel extension. Then came 5.5 inches of barrel curved at a precise 30-degree angle, and finally, 4.5 inches of straight barrel extending beyond the curve where the bullet would exit. Imagine taking a steel pipe and bending it like a hockey stick, except this pipe needs to contain a bullet traveling at supersonic speed, channeling forces that would tear apart lesser metals. But the barrel was only half the system. Mounted behind the curve was a periscope mirror assembly, offering 1.5 times magnification and a 12-degree field of view. A front sight sat at the tip of the curved barrel. A rear sight was positioned behind the mirror so the shooter could maintain a natural cheek weld on the stock while aiming through the periscope. What this meant tactically was extraordinary. A soldier could crouch 20 centimeters, about 8 inches below the top of his cover, see his target through the mirror, align his sights, and fire. His head, his shoulders, his entire body would remain below the parapet. To the enemy, the foxhole would appear empty, and then bullets would start coming from it. Small vent holes were drilled along the curved section of the barrel, designed to bleed off excess gas pressure as the bullet navigated the turn. Think of them as pressure relief valves, the barrel's way of breathing out before it explodes. On paper, this was a defensive soldier's dream. In reality, those vent holes were barely a band-aid on a hemorrhage. But the engineers did not know that yet. The Krummlauf was designed with an expected operational lifespan. The engineers projected it could handle sustained use in the field. They ran the math, tested the metallurgy, and arrived at a figure they believed would make the Krummlauf viable for frontline deployment. That number, and what actually happened when bullets started flying, is a story we will get to. And it is not pretty. But first, the Krummlauf had to be built, and building it required solving a problem that nearly killed the project before it ever left the workshop. This elegant design did not emerge fully formed. Its development involved a false start that nearly doomed the entire project. The initial assumption was reasonable on its face. Engineers believed that a standard 8mm rifled barrel could not survive being bent into a curve. The forces involved, A bullet slamming into a curved interior wall at supersonic speed would crack, warp, or shatter a barrel of matching caliber. The metal simply was not strong enough to contain the asymmetric pressures generated when a projectile is forced to change direction at over 2,000 feet per second. So their first solution was counterintuitive but logical in its own way. They used a larger barrel. Early prototypes mounted a curved 20mm barrel onto an 8mm rifle. The idea was that the oversized bore would act as a trough. The bullet would rattle through the larger tube, bouncing along the inner curve like a marble in a half-pipe, losing energy to friction but surviving the turn. Picture an assault rifle with a drainpipe bolted to its muzzle. It was ugly, unwieldy, and the ballistic performance was exactly what you would expect from a bullet tumbling through a tube twice its diameter. Terrible. The bullet exited with no spin, no stability, no accuracy beyond a few meters. It was a proof of concept that proved mostly that the concept needed a completely different approach. But then the engineers tried something that should not have worked. They tested a standard diameter 8mm rifled barrel manufactured using a technique called cold forming, applied after the rifling was cut. Cold forming the barrel post-rifling meant the metal was worked at low temperatures, well below the thresholds used in traditional hot forging. This process increased the steel's density, its hardness, and critically its resistance to the extreme stresses of a curved path. The grain structure of the metal was compressed, tightened, made more resistant to the microscopic fractures that would propagate under repeated impacts. The result defied their expectations. The standard diameter barrel outperformed the oversized trough in every measurable way. The bullet maintained better contact with the rifling grooves, spun more consistently as it navigated the curve, and the barrel held up longer than anyone had predicted. The very thing they assumed would fail. A tight-fitting, curved barrel turned out to be the answer. The bullet did not need room to tumble. It needed to be gripped, guided, forced around the bend by the rifling itself. This was a genuine engineering reversal, a moment where testing overturned theory and opened a path forward that no one had anticipated. With the barrel problem solved, or so they thought, the project expanded rapidly. With the infantry model taking shape, Germany's weapons developers began imagining the Krummlauf on armored vehicles, and the reasons were compelling. Every tank crew in the war knew the terror of close infantry assault. A soldier with a Panzerfaust, a magnetic mine, or a satchel charge could approach from angles that the main gun could not depress to cover. Dead zones existed around every armored vehicle, especially at close range. Blind spots where the hull-mounted machine gun could not traverse and the turret could not rotate fast enough. Infantry swarming these dead zones had destroyed hundreds of armored vehicles on the Eastern Front alone. Vehicle variants of the Krummlauf were designed at 30, 45, and 60 degrees of curvature. And then there was the most radical variant of all, designated Versatz P, featuring a full 90-degree bend. Imagine a barrel that points straight down from inside the tank, then bends at a right angle to fire horizontally outward. When not in use, it could be stored vertically inside the hull to save space, tucked away like a periscope. When enemy infantry swarmed close, the crew could deploy it through a hemispherical ball joint mounted in an armor port, a steel socket that let the barrel swivel and cover the vulnerable zone around the vehicle. One specific platform was identified for this system, the Elephant tank destroyer, a massive, heavily armored beast notorious for its vulnerability to close-range infantry attack due to its near-total lack of secondary armament. A 90-degree barrel, a bullet that turns a right angle. The physics are staggering, and the lifespan of that barrel was going to be measured in minutes, not months. The ambition was scaling faster than the metallurgy could support. But in 1944, ambition was all Germany had left. Now the perspective shifts from the workshop to the testing range. The infantry Krummlauf is ready. It clamps onto the St. G44 with a mechanical precision that belies the violence it is about to channel. The periscope mirror is aligned. The cold-formed barrel gleams under workshop light, its curve almost elegant, like the neck of a steel swan. Everything about this weapon is a bet against physics. Every round fired will be a negotiation between the bullet's momentum and the barrel's structural limits. The engineers have placed their wager. Now it is time to pull the trigger. What happened next would define whether the Krummlauf was a breakthrough or a catastrophe. And the answer came faster, much faster than anyone expected. The first round exits the curved barrel with a sharp, unnatural crack, different from a normal rifle shot. A pitch that carries a metallic edge, as if the sound itself has been bent. There is a hiss of gas escaping through the vent holes, a puff of propellant residue venting sideways like steam from a cracked pipe. The barrel rings with a faint harmonic that straight barrels never produce. The bullet hits the target. It works. For a moment, a single, fleeting moment, the Krummlauf is everything it promised to be. Aimed fire from total cover. A bullet that turned a corner and struck where it was pointed. But even on the first magazine, something is wrong. The barrel heats faster than a standard SAIT G44 barrel. The curve concentrates stress in ways that straight barrels never experience. Every bullet that enters the bend has to change direction. And changing the direction of a supersonic metal projectile means transferring enormous force into the barrel walls at the apex of the curve. Think of it like this. If you try to bend a garden hose while water is flowing through it at full pressure, the hose bulges at the bend. Now replace the water with a lead-core bullet traveling at 2,200 feet per second, and replace the hose with a steel tube. The bulge becomes a crack. The rifling inside the curve begins to erode. Each bullet scrapes microscopically more metal from the grooves. The rifling that gives the bullet its stabilizing spin is being ground away by the very bullets it is supposed to guide. After 50 rounds, the accuracy begins to drift. After 100, the groupings open up like a shotgun pattern. The bullet is no longer spinning cleanly. It is wobbling, yawing, tumbling out of the muzzle like a knuckleball. The barrel that was supposed to bend physics is being bent by it instead, slowly, round by round, cracking from the inside out. The engineers had calculated a specific lifespan for this barrel. They believed it could survive 6,000 rounds. 6,000. What they got was something very, very different. Let that number sit for a moment. 6,000 rounds. For context, a standard military rifle barrel, a straight one, can last anywhere from 10,000 to 20,000 rounds, depending on caliber, barrel material, and rate of fire. The Krummlauf engineers were not asking for miracles. They were asking for a barrel life roughly 1/3 to 1/2 of a conventional barrel. Given the extraordinary stresses involved, 6,000 rounds seemed like a reasonable, even conservative target. They had done the calculations. They had tested the metallurgy. They had cold-formed the steel. They believed the number was achievable. The 30-degree infantry variant, the primary model, the one closest to production, lasted approximately 300 rounds. 300, not 6,000. 300, that is 5% of the projected lifespan. 5%, 300 rounds is roughly 10 magazines on the SAIT G44. In a sustained firefight, a soldier could burn through 300 rounds in under 15 minutes. The Krummlauf was not a weapon you could rely on for a day of combat. It was a weapon that would be dead before the morning was over. In 15 minutes of sustained fire, the Krummlauf's life was over. 300 rounds that proved the laws of physics do not negotiate. And that was the best performing variant. The 45-degree variant, designed for vehicle mounting, survived approximately 160 rounds, 5 magazines, in a heated engagement that is measured in minutes, not hours. The steeper the curve, the faster the death. Every additional degree of bend multiplied the stress exponentially. The 90-degree Versatz P variant, the one designed to turn bullets at a right angle, likely had a lifespan so short it barely qualified as a weapon at all. The failure mechanism was not a single point of catastrophe, but a cascading series of destructions happening simultaneously inside the barrel. The bullet itself physically deformed as it was forced around the curve, flattening on one side against the inner wall, losing its carefully designed aerodynamic shape. A bullet that enters the curve as a precision projectile exits it as a misshapen lump of lead and copper. The rifling erosion was relentless. The curved section acted like a grinding wheel, each round stripping away the lands and grooves that are supposed to impart spin. Without spin, the bullet has no gyroscopic stability. Without stability, the bullet tumbles. Gas pressure spiked at the curve's apex, those vent holes relieving some of the buildup, but nowhere near enough to prevent structural fatigue in the barrel walls. And finally, microfractures propagated from the inside of the curve outward, tiny cracks that grew with each round until the barrel failed catastrophically. After 300 rounds, the barrel's interior looked like a ravaged mine shaft, the rifling scored and pitted, the metal discolored from heat stress, hairline cracks spiderwebbing through the curve. The barrel was not worn out. It was destroyed. Even before the barrel failed mechanically, the Krummlauf failed tactically. Beyond close range, the kind of distances measured in rooms, not fields, accuracy degraded to the point of uselessness. The bullet exited the curved muzzle with a pronounced wobble, a side-to-side yaw caused by asymmetric forces during the turn. At 50 meters, you might hit a man-sized target. At 100 meters, you might hit the wall behind him. At 200 meters, you were firing a prayer. Compare this to the St. G44's normal capability. The weapon was designed for accurate aimed fire out to 300 meters. The Krummlauf reduced its host weapon to a close range-only device, essentially converting an assault rifle into an inaccurate submachine gun with a self-destructing barrel. Those vent holes that were supposed to manage pressure also bled off propellant gas that would otherwise accelerate the bullet, reducing muzzle velocity and further degrading both range and terminal effect on target. So what you have is a weapon that cannot shoot straight, cannot shoot far, and cannot shoot for long. And Germany was diverting wartime resources to build it. In a static defensive position, a foxhole, a trench, a reinforced window, the Krummlauf could theoretically provide a few minutes of close-range suppressive fire from complete cover. That is not nothing, but it is a far cry from the war-changing defensive tool the engineers envisioned. History's most imaginative infantry weapon turned out to be history's most fragile. It was a gimmick with an expiration date measured in trigger pulls. But this is not where the story ends, because when the war ended, the Krummlauf crossed the Atlantic. When United States forces overran German positions and weapons depots in 1945, they found Krummlauf prototypes among the captured materiel. These strange bent barrels, looking like something a mechanic had dropped and forgotten to straighten, were tagged, crated, and shipped to Aberdeen Proving Ground in Maryland. Aberdeen was America's premier weapons testing facility, a sprawling complex of firing ranges, ballistics laboratories, and ordnance bunkers where every captured enemy weapon was systematically dismantled, studied, and tested. If you wanted to know what a weapon could really do, stripped of propaganda and engineering optimism, you brought it to Aberdeen and you fired it until it broke. Then you wrote a report about how it broke. The Americans did not just test the Krummlauf itself, they tested the concept. They wanted to answer a question that the German test data alone could not definitively resolve. Was this a good idea poorly executed by engineers working under wartime constraints? Or was it a fundamentally bad idea that no amount of engineering could rescue? They mounted curved barrel attachments on American weapons. The M3A1 grease gun, a .45 caliber submachine gun, the cheapest, most expendable automatic weapon in the American arsenal, a stamped metal bullet hose that cost less than $10 to manufacture, and the M1 carbine, a .30 caliber light rifle, standard issue for officers, drivers, and support troops across every theater of the war. The Americans got the same answer the Germans got. The curved barrels wore out catastrophically fast. Accuracy was abysmal beyond point-blank range. The concept did not fail because of German metallurgy or German manufacturing tolerances or the specific properties of the 7.92 Kurtz cartridge. It failed because of physics. A bullet traveling at supersonic speed does not politely turn corners. You cannot repeatedly force a supersonic projectile through a curve without destroying the barrel that contains it. No amount of cold-forming vent holes or alloy refinement can change that fundamental reality. The Americans closed the file. The Krummlauf was not a breakthrough waiting to be perfected. It was a dead end. Imagine being the American ordnance officer writing that report. You have just tested the most imaginative infantry weapon of the war. You have watched bullets fly around corners, and your conclusion is a single word: impractical. No branch of the United States military adopted any form of curved barrel technology. The project files went into storage. The concept was shelved permanently. What followed was not a breakthrough, but a masterclass in the distance between concept and reality. The Krummlauf was dead. But what did its brief, violent life actually mean for the war that spawned it? For all its ingenuity, the Krummlauf saw almost no real combat. There is no evidence of mass production, no confirmed record of a Krummlauf-equipped unit turning the tide of an engagement, no battlefield reports describing curved barrel fire surprising an Allied assault force. The weapon existed almost entirely in the realm of prototypes, limited test batches, and experimental units that were never deployed in sufficient numbers to affect any outcome. A handful of Krummlauf attachments may have been issued to frontline troops in the final months of the war, but by then Germany's military was in total collapse. Supply lines were shattered. Ammunition was scarce. The soldiers receiving these experimental devices likely had far more pressing concerns than testing a barrel that would be useless after 10 magazines. The Allied troops attacking those positions likely never knew a curved barrel was pointed at them from behind a parapet. It barely mattered. The vehicle variants fared no better. The Elephant tank destroyer, one of the intended platforms for the 90-degree Versatz P, was produced in a total quantity of approximately 90-10 units and suffered catastrophic losses on the Eastern Front long before curved barrels could have been fitted in any meaningful number. The problem the armor variants were designed to solve, infantry swarming into a tank's dead zones, was being addressed more effectively by the simple expedient of adding conventional machine guns and improving infantry armor coordination. The Krummlauf was an answer to a real question: how do you shoot without being shot? But it was the wrong answer, delivered too late, to an army that no longer had the luxury of wrong answers. And the resources it consumed? Those may have been the Krummlauf's most lasting wound. Germany in 1943 through 1945 was a nation hemorrhaging industrial capacity. Allied bombing had devastated factories across the Reich. Raw materials, specialty steel, tungsten, chromium, the exotic alloys needed for weapons manufacturing, were in critical shortage. Every ton of high-grade steel diverted to Krummlauf barrel production was a ton not used for tank armor, artillery tubes, or the standard rifle barrels that frontline troops desperately needed. The engineering hours were arguably even more costly. The metallurgists, machinists, and ballistics experts working on the Krummlauf were among Germany's most skilled weapons engineers. Every hour they spent cold-forming curved barrels and calibrating periscope mirrors was an hour they did not spend improving weapons that actually worked, weapons that could be produced in quantity, weapons that would last longer than 15 minutes of combat. This pattern extended far beyond the Krummlauf. Germany's late-war weapons development was riddled with wonder weapon projects. The V-2 rockets that consumed more resources than the entire Manhattan Project for negligible strategic effect, the jet fighters that arrived too late and in too few numbers, the guided bombs and acoustic torpedoes and rocket-propelled grenades that each represented genuine engineering brilliance deployed in service of a losing strategic position. The Krummlauf did not lose Germany the war, but it is a perfect miniature of how Germany lost the war. Brilliant engineering in service of strategic delusion. Could the Krummlauf have worked if Germany had more time, better materials, or a less desperate strategic situation? Almost certainly not. The fundamental physics of forcing a bullet through a curve impose limits that no amount of engineering refinement can overcome. The barrel will always wear out orders of magnitude faster than a straight barrel. The accuracy will always degrade. The concept has a ceiling, and that ceiling is very, very low. No mass production, no battlefield impact. No adoption by any post-war military. The Krummlauf is a footnote, but a fascinating one. The anonymous engineers who built it were likely dispersed after the war, some absorbed into Allied weapons programs, others returning to civilian engineering, their work on the Krummlauf a strange footnote in careers that may have included far more successful projects. The American testers at Aberdeen who documented its failure left behind dry clinical reports that captured the death of an idea in the precise language of muzzle velocities and barrel fracture points. And the Krummlauf itself, a handful of surviving examples, sit in museums and private collections, including one at the Military History Museum in Koblenz, Germany, where it rests behind glass, its curved barrel frozen in a permanent question mark. But the Krummlauf's story did not end in a filing cabinet at Aberdeen. Its ghost has haunted popular culture ever since. The 2008 film Wanted, starring Angelina Jolie and James McAvoy, popularized the idea of curving bullets, assassins who could bend bullet trajectories through sheer force of will, flicking their wrists during firing to send rounds arcing around obstacles. Pure fiction, physically impossible, but the visual DNA of that fantasy traces back to real experiments like the Krummlauf. The weapon appears regularly in video games, military history forums, and every list of weird weapons of World War II ever compiled. It has become a symbol of creative desperation, the kind of invention that makes people stop scrolling and say, "I cannot believe they actually tried that." Military historians have consistently characterized the Krummlauf as a folly, an example of Nazi over-engineering, the systemic tendency to pursue technically complex solutions to problems that had simpler, more practical answers. But there is nuance worth acknowledging. The question the Krummlauf tried to answer, how does a defender fire without exposing himself, is entirely legitimate. It was legitimate in 1943, and it remains legitimate today. Modern militaries have addressed it not with curved barrels, but with remote weapon stations, camera-guided fire control systems, drone-dropped munitions, and robotic platforms that remove the human operator from the line of fire entirely. Germany was trying to solve a 21st-century problem with 1940s technology. The concept of corner shooting has even resurfaced in modified form. The Israeli corner shot system, developed in the early 2000s, uses a pistol mounted on a hinged frame with a forward-facing camera, allowing the shooter to aim and fire around corners electronically. No curved barrel needed, no physics violated. The Krummlauf's goal survived even as its method was abandoned forever. A barrel that bends, a bullet that turns a corner, a soldier invisible behind his cover, firing at enemies he sees only through a tiny periscope mirror. It worked for about 15 minutes, 10 magazines. Then the barrel cracked, the rifling disintegrated, and the soldier was left holding a rifle with a useless metal appendage clamped to its muzzle. The age of the curved barrel ended not in a single afternoon, but in a slow, grinding accumulation of cracked steel and tumbling bullets, repeated at testing ranges in Germany and Maryland, until no one was left who believed the next round might be different. The Krummlauf is proof that the most dangerous gap in engineering is not between concept and prototype. It is between prototype and reality. If this story surprised you, subscribe. There are more weapons, battles, and engineering disasters where this came from.